All right. I think we've got the first batch of people. Others will be trickling in every now and then, I guess. I'm going to have an eye on this. I'm going to admit some more people here. But first of all, hi. Really excited to have all of you here. My name is Eric. I'm the, I don't know, lead coder on KrigR, I would say, but that sounds too grandiose. It's a brainchild I've really grown fond of, and I hope other people will like it too. And to find that out, I've invited all of you, and I'm very happy that this many of you have just shown up for it, to this kind of 3-hour session where we will give you a bit of background, we being Richard and I, on how we got started on this, what kind of theory went into this R package, and how you can then execute it with a few R examples along the way. We'll hope this will be very helpful to you guys. If you have any kind of questions, input, don't wait until a talk or a session ends, just let us know immediately. We'll go right into a lecture by Richard here in a second. During that, if you would be so kind as to direct your questions towards me in a private message, I will then immediately interrupt Richard with it. This is just so that every time something pings in the general chat, he doesn't get distracted by it. And with that, we are actually already on Richard. Richard's a climate scientist and a very good friend of mine who works at the Nansen Center in Bergen, which is where he's zooming in from today. During my master's thesis, I first encountered Richard, and he told me about all of the fantastic climate data that was out there that I just wasn't aware of and or wasn't using, and made me reconsider quite a few of my biogeographic study setups, where I have now been converted entirely back from gridded observation datasets to climate reanalysis datasets, and that's also what motivated me to write this KrigR program. So with this, I'm giving this over to Richard because he, even after about a year or so of working with him, still does such a better job of explaining everything climate related than I ever could.
All right, thanks, Eric. Yeah, okay, so 1 second. Okay, so this is going to be a brief introduction into climate data. And as Eric kind of mentioned, this is a lot of this was sort of lessons learned working with Eric over the last couple of years about what's important to know and to understand about what data is out there, what data is available, and what the sort of best practices for making use and misuse of the data. So I'm going to start by taking a review on climate data itself, just to review what sort of types of climate data are out there, and what are the sort of advantages and disadvantages of using each type of data. And then we'll go into downscaling methodologies. So it's still the major problem with a lot of these data sets is their very coarse resolution. So we've got a few different methods for downscaling that. And we'll talk, of course, particularly about kriging, since that's what we'll be doing with this afternoon. We'll go into a little bit of detail about how kriging works, and in particular, how to best choose, make good choices to get the most out of your downscaling your data. And the last section, I want to talk a bit about climate models, because there was a lot of, I think it's very easy to get a bit lost in all the climate model data out there, and to understand climate projections, climate predictions, what are the important things you need to know about them, and how you can best make use of climate model data. So as Eric mentioned, I guess many of you are familiar already with gridded observation data sets. So these are built up from single location station measurements, and they're aggregated and then interpolated in some ways to create a gridded product. So one of the things you might get a bit lost in is all the different options there are out there already for gridded observations. So this is just, we compiled a list here. I think we are going to share these presentations later, so, and all of these links, so you'll be able to follow through and get any of this data if you're interested. But all these are generally a pretty coarse spatial resolution. So most are sort of 5 degree, and coarse temporal resolutions as well, sort of monthly resolutions. And the reason for that is because station data is pretty sparse. And so you need quite coarse grid cells in order to be able to incorporate as many stations as possible, so that you can cancel out the biases and the drift problems you get individual stations. And also with when it comes to temporal resolution as well. So if you want sort of high resolution daily data, that's quite a challenge to get reliably purely from station data. So the major shortcomings, I'd say, of gridded observations is that you get quite limited coverage. Certainly going back in time can be quite an issue, pre sort of 1970s, and they are each of them subject to their own biases. So there's an awful lot of uncertainty that comes into the methodology about how you go from the stations to the gridded product. So that this is a process of homogenization, and you have to make choices about how you do that. So there can be a bit of uncertainty that comes into that. Not so much in the modern era. If you're interested in data sort of 1970 onwards, they can be quite reliable globally at least. But going back in time, it becomes more of an issue. And also there's an awful lot of uncertainty that comes in the different interpolation methods that are used in these different products as well. So digging through all of these and understanding how they're different and why they're different is quite a challenge in itself. But one of the other problems you can have is, so this is data sets for both temperature and precipitation, is that you can have inconsistencies between the data sets as well. So some of them, for example, might be derived from satellite data, some of them from station data. But you can have dynamical inconsistencies between how much precipitation you're getting, for example, and how much and the temperature anomaly at a given point. So these because of the different methods applied to the different data sets, these things can be inconsistent. So just to give an example of that, this is the station data that goes into WorldClim. So you can see, of course, like in the US and much of Europe, we've got very high station data density. But as soon as you start going outside of that, it's extremely sparse data. So if you're interested in regions in Siberia, for example, you probably should wonder, how useful a station is to you if it's 1,000 kilometers away from the site you're interested in. It's probably not that representative. So accounting for spatial representativity of stations is quite an important one when you're trying to turn station data that's scattered like this into a nice gridded product. So what I want to talk about is a better way to do this, and that's using reanalysis. So this is a way to combine observations and dynamical models, so weather models, using data assimilation to get our best guess at past climate. So reanalysis are really widely used in climate science. I had a quick look, and about 30% of the papers from last year cited a reanalysis in their study in some way or another. So the reason they're taken up so widely is because they use the data assimilation to make optimal use of the observations. And they also have the advantage that they are dynamically consistent as well. So the basics of how they work is you have your model. So that's your forecast model, dynamical model used to make predictions. And you run that multiple times, so you've got an ensemble, and that gives you some spread. And then you take your observations and you use data assimilation to make an analysis to get something which is both consistent with the observations and with your dynamical model. So as a result, you end up with a gridded product, which is dynamically consistent at all locations. Now, there's quite a lot of different reanalysis products out there. We'll take a review of that in a second. But the main differences between them come into which observations they use. So, for example, they might just use surface-based observations, or they might take everything they can get their hands on, so surface-based or satellite or whatever they can. And the second way in which they're different is the assimilation method they use. So there's different ways of doing the data assimilation, and that can make quite a big difference to your analysis as well. And the third way they deviate is in the skill of the forecast model. So just quite simply, some models are better than others. So that can be an important difference between reanalyses as well. But in short, what they provide you is a global product which is consistent and from which you can get an awful lot of different variables as well. So in that way, it's kind of described as sort of a synthesis of models and observations. And this is just a review of some of the global climate reanalysis products that are out there. So already these come at a higher spatial resolution. So for example, a lot of what we'll be using, I think this afternoon, is 05 land, which is already at 0.1 by 0.1 degree resolution. But the major difference with the observational data sets is the temporal resolution as well. So because this is a dynamical model, you can extract data at any temporal frequency you like. So the data is actually output hourly. So you can get hourly resolution, surface temperature, precipitation, soil moisture, whatever you're after. And currently this reanalysis goes back to 1950 as well. So most of the reanalysis, the resolution, temporal resolution is subdiurnal. So you get sort of either hourly or 6 hourly at the most. But so the big advantage of this is that you can get all the different climate parameters you're interested in from a single product. And in that way, they're also consistent as well. You will not have the problem of combining different data sets. And of course, the major advantage is that they are global products, so there is no spatial or temporal gaps in the data either. And they provide, of course, a very close match to a huge range of observations. So if you're comparing them to satellite observations or ground-based observations, you'll find a very good consistency between all these different products. But it corrects for the bias. They also automatically correct for the biases and the drift and the other problems you can get with individual observations. But as well as these global reanalysis, it's becoming more popular to do regional reanalysis as well. This is just to push the envelope in terms of resolution. So one example here is we have a regional reanalysis called UERA for the European domain. And this is built using global reanalysis to force the boundary conditions. And then you run a higher resolution dynamical model over a limited domain to get a higher resolution reanalysis product just for the European region. So the major advantage of doing that is, of course, just pushing to higher resolutions. So there's a couple of data sets that I've linked to here. Probably the most useful one is the European one that's currently at 5 kilometer resolution. So as I mentioned, one of the major advantages of reanalysis is that you can get all your different variables from one location. So these products all have all the different essential climate variables available for them. So this is a list of different variables which are considered important in terms of monitoring the climate, but then they got extended to include the biosphere and ocean as well. So you can find this list here. This is a list of all different essential climate variables. And they're chosen based upon their importance in terms of their feasibility for how easy it is to measure them. And of course, so it's basically a prioritized list of which variables we target for observations. So it has to be cost effective as well. So I think if you go through this list, you'll find an awful lot of, I think you'll find all the variables you're interested in for your studies. So I mean, there's the obvious ones like air temperature and precipitation, but also surface radiation budgets, and then an awful lot of terrestrial variables as well. But if you do find that you're interested in something which isn't there, this is an interactive process. So it's an iterative process with the WMO. You can go to this website, you can say, I think we need this variable and this is why, and they can consider adding to the list of climate variables. But the problem we mentioned with even with these regional analysis is that 5 kilometers is probably still quite coarse in terms of the resolution that you're after. So that's why we focus on downscaling as well. And there's 3 basic different ways of doing downscaling. So bringing that low resolution climate data to the sort of resolutions that you're interested in. The first one is doing dynamical downscaling. So this is quite simply, you take You take your boundary conditions from a global reanalysis, and you run a dynamical model over a small domain. And this helps you, and then you get your variables at a higher resolution. But the major issue with doing this is that every dynamical model you use has its own problems. It has its own biases. It has its own limitations. So you introduce uncertainty based upon the dynamical model you use. So in the last 10 years, we've had various different comparison programs to run different regional dynamical models to try to understand the sources of uncertainty in regional climate. And here you can find a whole host of data for different regions. So this is but the major issue here is that you're introducing more uncertainty from the dynamical model as well. You can also use purely statistical methods. So that's what we'll be talking about with KrigR this afternoon. So this is where you exploit known relationships between different variables. So if you know a variable to a higher resolution, you can exploit the statistical relationship to bring your climate variable down to a better resolution. So this is just an example from Eric's work back in his master's. He was starting with air temperature of Spain and France and bringing it down to higher resolution to match his NDVI resolution. So the way we chose to do that was using KrigR. This is just a schematic showing you how that works. So it's essentially a Gaussian process, random walk process, exploiting the covariance, spatial covariance. So then it defines both an estimate at the higher resolution as well as the uncertainty associated with that estimate as well. So this is why we choose KrigR for our statistical downscaling. But in addition to that, we can also use hybrid methodologies. So we can combine dynamical downscaling with statistical downscaling. And this is particularly useful when you have very sparse observations or you're trying to get to very high resolution in very complex terrain. So this is actually an example from our studies of air pollution in Bergen in Norway. So we have how many is it? 7 different stations around the city where we monitor the wind speed and temperature and air pollution. And then this is of course very sparse observations. If you just did a straight interpolation between them, you get a very smoothed out map. But we combine this interpolation methodology with a dynamical model. So very high resolution, sort of 10 meters or so, to simulate the airflow around the city. And then we can get something that is a very good fit to the station data, but also is a much more realistic explanation of the flow around the city as well. So you can see these are the mountaintops here. And this is the valley floor where most of the urban environment is. So this is very useful also when you're trying to get to very high temporal resolution. So you're interested in, or when the relationships between the different stations change depending upon the large scale state. So for example, you can understand how when some of these relationships are flow dependent, so you can use this hybrid dynamical method to resolve that.
Interruption here.
Yeah.
We've got a question from Jason asking how the dynamical models are combined with the interpolation results.
Yeah, so you do the KrigR using, and the model essentially provides an external drift for the KrigR. So the model is a full dynamical model for the atmospheric dynamical model for this domain, a high resolution, and that provides the background tendency for the KrigR. But this is this is a very nice way to go when you're interested in very localized effects, but it's also quite expensive because these very high resolution atmospheric models are not cheap to run. So it's a good thing to know about, but I think in practice it's quite a hard thing to do for many cases. So most people focus on purely statistical downscaling because that's what we do with KrigR. So this is, as I mentioned, this is KrigR. So this is exploiting the relationships with covariance to downscale across different resolutions. And this is an example we took the ERA 5 land data, so starting at 0.1 degree by 0.1 degree, and we brought it down to a 1 kilometer resolution. So we did that globally. That took quite some time. And if you zoom in, for example, on northwest Scotland, where there's some very interesting geography, you can see how how much detail you can get in the temperature across this kind of domain. But as I mentioned, the nice thing with KrigR is, in addition to the estimate, you also preserve the uncertainty from the process as well. So you can see the estimate here. You've got about 3 degrees of variance across the domain. That's just because it was a climatology. And the uncertainty is about an order of magnitude lower than that. So you can see the uncertainty peaking. You're probably not familiar with the geography here, but the red spots are all the highest mountains. So you get increased uncertainty over the highest mountains. And that's because the relationships are derived based upon the training resolution. And if you're extrapolating beyond the range of the training resolution, of course, you're going to have higher uncertainty. So these red spots are here as where we have elevations greater than there was in the training resolution. So this can be very useful if you understand that there's some strong relationships between the variable you're interested in and a covariate, which you have a higher resolution. So a very obvious one is between temperature and elevation, for example. We know these things two things are closely related. And most importantly, they're also very closely related at almost every time scale as well. So whether you're looking at hourly data or daily data, yearly data, or climatologies, you're going to find a tight relationship between temperature and elevation. So this is the resolution we started with on the left. And this is the covariate data, so the elevation data at that resolution and at the target resolution. So using this covariate data, we can then move towards, the final product is this downscaled surface air temperature. So this works well because the temperature explains very well, the elevation rather explains the variance in the temperature across this domain very well. So that's an example of a very strong relationship between your climate variable and your covariate. But an example of a weak relationship, for example, would be with precipitation and elevation. And you might think that's a surprise because in some ways elevation does define where you get precipitation. So for example, if you have a very important feature is orographic driven precipitation. So you're going to get more rain on the west coast than the east coast, for example, simply because that's you're forcing the dynamics of the model. But when we try to downscale precipitation, so when we go from the coarse resolution and we use the same covariate, the elevation, all we get is just a smoothed out map of the precipitation. And that's because the relationship between precipitation and elevation is not a statistical one. It really depends upon the dynamics as well. So if you think about what covariates might be useful for downscaling precipitation, it's mostly going to be related with atmospheric variables. There's not something you can take from a terrestrial product, which is going to explain the variation in precipitation. But what you can explain better is the variations in soil moisture. So for example, we might expect that soil moisture is related with elevation, but also with how steep the slope is and the soil properties as well. So this is an example of downscaling taking the coarse resolution soil moisture, and we use the elevation data, but we also use the soil properties and a function which described how steep the slopes are in the terrain as well. So in contrast to the precipitation, we can get then a very high resolution map which reasonably captures the variation in soil moisture across the domain. So just to flip back and forth there, if you're trying to downscale precipitation and if you're trying to downscale soil moisture. So because the soil moisture depends much more on terrestrial covariates like the soil properties, the slope steepness, things that are fixed in time, then you can have a much better, you'll be able to downscale soil moisture much more effectively than you can downscale precipitation.
Just to quickly jump in on this, just to highlight for the more biology-minded people in the room who are used to more the gridded observations being used so far, this problem of downscaling precipitation is not unique to what we're doing here. This is a problem all climate data sets are facing, and which makes the downscaled precipitation maps available in many gridded observations, such as WorldClim, in rather undersampled regions, pretty unreliable, I would say. And we would just like to show you how soil moisture may give you the same biological component here into your study, but at a much more reliable resolution and data accuracy. Sorry.
That's good, thank you. Yeah, that's a good point. So the way I would think
sorry,
about it is
we've got a question from a question from Jonathan. Where does the soil moisture come from?
The soil moisture comes from the reanalysis. So this is taken it's taken from a model. It does have limited station observations to constrain it, but it is a dynamical model. So you use a dynamical model to describe the evolution of the soil in time, in terms of it's the temperature and the humidity within the soil. And that uses these terrestrial covariates. So it uses the soil properties and it uses the terrain definition from the elevation and the steepness to define how the moisture goes through the soil, how much runoff you get. So you have the precipitation coming in the dynamical model, and then it describes how much gets transferred to runoff, how much gets absorbed into the soil. So how I think about it is that if you want to downscale precipitation, you really need a dynamical model. It is fundamentally, you cannot do statistical downscaling of precipitation in a meaningful way, because you do not have meaningful covariates to explain the spatial variation. But when it comes to soil moisture, you do have, because it comes down to the terrestrial properties. So just to show you an example of what happens when you introduce different covariates, this is the downscaled surface temperature. And I used covariates of just the elevation plus a description of the slopes, and the elevation, the slopes, and the aspect as well. So which direction the slopes were facing, north, south, east, or west. So just visually, you would expect, you can see there's not that much difference in the estimates. A lot of the relationship comes down to the elevation, so that really determines it. But if we look at the differences, so if we look at the difference in the estimate using the elevation and the slopes minus the elevation, you start to see some subtle differences. So again, if we look back here, there's about a 5-degree variation across the whole domain. And the difference of adding slopes as a covariate changes that estimate by up to about ½ degree or so. And that's mostly across the high mountains. And that's because the elevation and the slopes are tightly linked. If you have higher elevation, you're more likely to have steep slopes. So these things are correlated. So that's why the estimate changes a little bit when you introduce slopes. But when you introduce the aspect as well, it has a very subtle effect. So it's almost no difference to your estimate actually. It's a subtle difference in values, but it's very small compared to the effect of accounting for slopes. So there's a lot that depends upon your choice of covariates. So we know, for example, that elevation is extremely important for temperature, and we speculated that slopes are also important, that the direction of the slopes is also important. But when we test them out, we find that they don't make that big a difference to the estimate. But they do also change the uncertainty on the estimate as well. So if we look at the uncertainty with just the elevation over here, so it's very flat. So we get this very similar uncertainty in the estimate across most of the domain. When we introduce the slopes as well, we start to see an increase in the uncertainty, mostly across the high mountains. And then we see again a subtle increase in the uncertainty when we introduce the slope aspect as well. So again, if we look at the difference in the uncertainty, so in this case, red is an increase in the uncertainty, blue is a decrease in the uncertainty. So when we start accounting for slopes as well, we're actually decreasing the uncertainty across the coastal regions, but we're increasing it in the mountainous regions. Whereas when we introduce the slope aspect, we see a universal increase in the uncertainty. But I would point out the scale here. So the uncertainty across most of the domain is about 0.4. The added uncertainty from accounting for slopes is an order of magnitude less than that, so about 0.04. And the difference of adding the aspect is even less than that. So these additional covariates subtly change the estimate of your temperature, as you can see here, and they also subtly change the uncertainty as well. But the clearly dominant relationship is with the elevation. So this is just an example for surface temperature, but this will apply to any downscaling you're interested in. Your choice of covariate will matter. So it's a combination of when it comes to choosing your covariate, there's some important things to consider. So just to show you the same for soil moisture as well. So we did 3 different downscalings of soil moisture, using again the elevation, the slopes, and the elevation, slopes, and aspect. Sorry, and soil properties. So the elevation itself actually doesn't explain that much of the spatial variance. It's when we introduce the slopes that it starts to explain a lot, as you might expect, because it strongly affects the runoff. When you introduce the slope, the soil properties as well, that also changes the estimate quite a bit. So you can see, for example, in some of the coastal regions where you start accounting for the differences in soil properties, you can get really quite differences in the estimate of soil moisture as well. So we can start to, from these, we can start to rank the importance of the different covariates as well, which is what we'll be doing later on. But this also changes the uncertainty in the estimates as well. So you can see that, again, we have a very flat uncertainty for the soil moisture. And you get these peak in uncertainty around the coast. That's just because we have differences in the land sea mask between the coarse resolution and the fine resolution data. And then when you start to introduce these other covariates, you increase the uncertainty as well. So particularly when you introduce the soil properties, you get a lot of uncertainty associated with those. So you're probably wondering at this point, like, what do I do? You know, which covariates should I choose for a given for my downscaling? And the answer is this is a combination of understanding the physics and of testing as well, because you might not know in advance what's going to be an important covariate. But there are a few pieces of advice I would give about this. The first step is that you should identify any known relationships you have. So for example, with temperature, we have known relationships with elevation, with slope, and slope direction. But also you should make use of the functionality as well. So if you know, for example, that the relationship with the covariate is nonlinear, you can include that in your kriging. So you should keep that in mind as well. And importantly, which we actually didn't do in those previous examples, is you should include the interaction between covariates. So where, for example, you know that elevation and slope steepness, these things are probably not independent, you should incorporate the interrelationship between those as well. And this depends a lot upon what domain you're interested in. So in order for your covariate to have any kind of explanatory power, it should of course have some substantial variation across the domain you're interested in as well. Because if it doesn't, it won't help you constrain the problem. And importantly, you should also make sure that the relationship you're thinking about holds on the timescale you're interested in. So as I mentioned earlier, temperature is associated with elevation at all kinds of timescales, but other variables might not be. So for example, we're going to make a prioritized list about these, which covariates you should use at different timescales. But for example, soil moisture at high temporal resolutions, like daily or finer, like hourly resolutions, this will mostly depend upon precipitation. It won't depend upon the soil properties themselves, because it doesn't have sufficient time to respond. And this especially is important when you go to, if you're interested in soil moisture depth as well, so like 0.5 meter below the surface. It'll take time to respond, so you won't necessarily have the same relationships at daily timescales as you'll have at monthly timescales. So that's another point you need to remember when you're choosing your covariates. But the final thing I would say is that you can also consider using a variable you've already downscaled. So for example, you can downscale your air temperature using these very strong relationships, and then you can use that downscaled temperature to KrigR another variable like humidity. An important choice here is also the radius you choose. So there's a parameter in the KrigR program called nmax, which defines the number of cells used from the training data around your grid point to define the relationships. So the broader, the larger nmax you choose, the wider the radius is from which you're creating your variogram, and you're defining your relationship between the climate variable and the covariates. So as you increase the nmax, as you increase the radius, your estimate of from your downscaling is going to start to converge. This is an example from downscaling surface air temperature. So the three different colors, three different timescales. The solid lines here, this is the mean absolute difference in the estimates, and this is from across the whole of the UK. So this is just taken for different values of nmax. So as you go to very small nmax, so like 15, you're taking a radius of about 15 kilometers or so around your grid point to define your relationships. So you've got quite big differences in your estimate. And as you increase the radius, you're going to get convergence of your estimate. So one of the things we're going to implement in KrigR is a recommendation for this. So you don't have to think about this problem, but to choose the optimum radius to define your relationship with your covariates. But as you increase that radius, you're essentially taking in more data from the training resolution to define those relationships. So your estimate is going to start to converge. Your uncertainty is going to decrease. But also importantly is that your computational time is going to increase exponentially. So this is another aspect you need to think about, is how fast you need your downscaling to work. So just to give you an idea of what that looks like, this is me doing the downscaling surface air temperature using just two different radiuses. So this is an nmax of 15 and 480. And this is radiuses corresponding to about 10 kilometers and 100 kilometers. So you can see the difference in the estimate. This is the difference in the estimate here. It mostly comes down to the terrain relationship. So there's large differences where you've got high mountains. And that's because the radius you're using to define the relationship, if it's very localized, then you're going to have a very different relationship between surface air temperature and elevation. Whereas if you take a very broad relationship, so the nmax of 480 covers most of the terrain, so you have one relationship between surface temperature and elevation for the whole domain. And then you have very robust estimates. So just to show you what the uncertainty looks like as well, because the more you shrink that radius, the weaker, the more uncertain the relationship is between the climate variable and the covariate. So you have much higher uncertainty. So the uncertainties here, of course, again, they're peaking in the high mountains, but they're an awful lot larger in general than the uncertainty you'll get if you take a very broad radius. Okay, that's enough about downscaling. I want to talk a little bit about climate models, though we don't have too much time. So I want to say that climate models have changed a lot over the years. So we've actually started to include an awful lot of different components into climate models. So you can find quite detailed descriptions of marine ecosystems, for example, but also there's a lot more detail included in terms of each of the different components. But one of the main things is, of course, we've been increasing the resolution over the years as well. So back in the mid-90s, your climate model resolution was about 200 kilometers. It looks something like this. And now we're at about 25 kilometers for a typical climate model. So we're starting to resolve an awful lot more of the detail. So they are starting to get to the point where it's quite useful, because when we're doing this downscaling, we can downscale by about an order of magnitude with some degree of confidence. So these climate models start to become quite useful for you for these. Now, there's an awful lot of, you don't, of course, don't have to run any climate model yourself. There's an awful lot of data out there already. So, of course, a lot of what we're interested in from climate models is either trying to understand, make projections about the future. This is just an example here from latest climate projections for the 21st century. Or we're trying to understand how important a given process is in the climate system. So with climate models, of course, we can just run them. We can run these sort of detection attribution studies as well to understand how important a given factor is in the climate system. Now, an important factor when it comes to climate projections is the uncertainty associated with them as well, because you see in these projections, this is your mean estimate and your uncertainty associated with that estimate, but that uncertainty is coming from different sources. So on short lead times, there's three different components essentially to the uncertainty. There's the scenario uncertainty, which is, well, for the 21st century, it's how much CO2 we emit. That's the major source of uncertainty. Then there's also uncertainty associated with the models as well. So how well we describe the different processes. And the third part is the internal variability in the climate system. So this is just, we have long-term variability over the scale of decades to centuries. And there's uncertainty associated in our future projections about what happens based upon that. So the relative importance of those different sources of uncertainty changes over time. If you're looking at short lead times, it really matters what the initial conditions are, where you start. That's essentially this internal variability. So this internal variability comes in because we don't define the initial conditions. We're just treating it as a boundary condition problem. So you have a lot of uncertainty that comes from that in the first sort of 20, 30 years. And then later most of the uncertainty comes from either the scenario or the model. So this can inform a little bit about what you can, what you can't use climate projection data for. So the important thing to bear in mind is that this isn't predictions. This is synthetic time series drawn from climatological distributions. So we're just sampling from that distribution different possible features. So this is also important when it comes to understanding how confident you can be in given projections as well, because how robust we can be in these projections depends upon which variable we're looking at, what sort of spatial scale we're interested in, and how fine a temporal scale we're interested in as well. So if you want to know how, for example, mean temperature changes on continental scales, this is something we can say with high confidence. But if you're interested in something much more localized, so for example, if you're interested in flooding in a given region, you might want to know how precipitation extremes are going to change on a country scale. And this is something that it's much harder to have confidence in from climate model projections. So one of the things we've been developing, because we're very interested in making predictions for the next 10 to 20 years, is starting to use climate predictions instead. So when we're using projections, that's purely a boundary condition problem. We're just saying how much CO2 is going to be emitted, how aerosols are going to change, but we're not interested in what the weather is today. We don't start from a given initial condition that we know. But in climate prediction, that's exactly what we do. So we prescribe the initial conditions, and then we try to predict what's going to happen in the next coming decades. And this is something that's very challenging for many reasons. There's different sources of predictability in the climate system, but it's quite hard to exploit them. So a lot of the predictability comes from the ocean, because the ocean is much slower to respond than the atmosphere or the terrestrial climate. So we can what we started to do is use the observations of the ocean state to make predictions about how climate is going to change on short timescales. So this is just an example to try to clarify that. So the blue run here, this is what you get if you make climate projections. You're simply saying how how CO2 emissions have changed over this period between 1950 and 2010. And you can see there's a general increase in this this property, but it's you can't predict for any given year what the value is going to be. Whereas what we're doing here with the red line is climate prediction. So we're simulating the observations using data assimilation to nudge the model, to force the model to fit the observations. And we do that up to 1990, and then we just run the model to make predictions about what happens in the next 20 years. And then we can make climate predictions from that. So this is starting to become, we start to have quite good skill in different aspects of this. Because the source of predictability is mostly in the ocean, this is much more reliable when it comes to predicting for the ocean as well. But we're trying to transfer that predictability onto land. So one of the things we've been doing with this is making forecasts for fish on sort of 10-year timescales. So there's some species of fish which follow salinity gradients, and we can predict the salinity gradients, so we can predict where the fish are going to be. So of course, these are probabilistic forecasts, but they are getting quite good, and they are quite important when it comes to making prediction for fishing quotas for the next 10 years or so. But in addition to these sort of 10-year predictions, we also have seasonal forecasting, which you're probably quite familiar with as well. So this is extending weather forecasting, but in this way we can use more sources of predictability. So we can use what's going on in the land to better predict how the climate is going to evolve on seasonal timescales. But again, this is very probabilistic. So this is just an example of what NOAA in the US produced to predict seasonal drought changes. But it can be useful for if you're interested in predictions for the sort of out to 6 to 10 month kind of range. So you probably want to know where to go and get the data as well. There's this very nice tool that was made by the Dutch Meteorological Institute for having a look at climate data. So it's a Python-based tool, web-based tool, and it's very useful for doing sort of quick analysis or for understanding multi-model projections. So you can go and select a given climate variable. So in this case, I chose the near surface temperature. You can look at a scenario for the 21st century, and you can take the difference, you can take a look at trends, and this analyzes all the current global climate models to understand how robust projections are for this, this given variable. So for example, here I was looking at median changes in precipitation between the end of the 21st century and recent history. And this is telling us the projected change and whether that projected change is significant based upon the multi-model ensemble. So as well as visualizing this data, you can also just go and grab this data as well. It's available in .NET-CDF format. So for most things, this is what I would recommend for getting your climate data, because it's very readily available. It's a very easy to use tool, and it'll get you a relatively limited data set, which is what you need. It is a bit limited in which variables are on offer, but there are quite a few. So this is another example. You can also choose for different regions as well. There's an example I made looking at soil moisture in Europe. Again, looking at median change between end of the 21st century and recent climate, but looking for the summer. So you can see the models make very robust projections about drying soil across most of Europe in the summer and over the next century. So this can be very useful just for understanding the core essence of a problem. If you want a sort of broad brush view on how climate's going to change for a given region and for a given variable. But and then of course you can go and grab the data and work with it. But the thing to bear in mind is that any time series you're pulling down from this is synthetic. So, and it will, each model and the ensemble mean of models as well has biases. So you'll need to correct that based upon observations. So both in terms of the spatial pattern and the temporal variability as well. So this is a very useful tool if you want to just get the multi-model mean, the sort of general projection about climate change. But if you want to get prediction data, or you want to get individual models, this is the tool to use. So you can head to this website and you can select from all the different experiments that have been run. This is a host of all the different experiments that have been run by the CMIT program. So this is a climate model intercomparison project. So you can find data from all different global climate models run around the world. Then this is experiments looking at how climate changes in the 21st century under different scenarios. You can get decadal prediction data from here, you can get paleoclimate data from here, and you can get all your different essential climate variables from here as well. And it's quite a friendly interface. It's a point-and-click interface, and you can download your data using wget scripts as well. It's quite efficient that way. So for getting all the data to work with yourself, this is your one-stop portal. Yeah, okay, that was it.
All right, thank you very much for that, Richard. I would motion we just wait for about 1 or 2 minutes here as everyone stocks up on tea, gets some questions out, and then I'm just going to take over and come in with a more biologist-focused mindset and tell you a bit more about the R package itself. And in the meantime, Richard and I will just switch screens here. Thank you very much for the talk, Richard. And yeah, we will pick this up shortly in just about 1 or 2 minutes, just so we can all stay hydrated here. I am never sure of how Zoom sharing works. You should be seeing a PowerPoint slide now, right?
Yes, yeah.
Lovely, thank you very much. Okay, I'm restocked on tea. We've switched the screens, and I think this is where we will now go into the package explanation here. So just bear with me. I'm just going to run you down right quick how the package should work, how I think people should interact with it, and how you might want to abuse it in the near future, of course. And first and foremost, give you a tiny explanation of why I think this is even important for biologists specifically. If you've got any questions, I'm just going to have an eye on the chat at the same time as I'm explaining this. Should take just about 20 to 30 minutes here, and then we're going to go straight into R itself, and I'm going to show you live how this works. So starting with this, what we need in biology, from my point of view, is some high-resolution data that explains the complex natural world quite well. So when I mean high resolution, I'm talking both space and time, whereas space has gotten quite a lot of attention over the recent decades, I would say, with people striving for higher and higher spatial resolutions in their data sets. Temporal resolution, I feel, has been the black horse so far and is really coming into climate change analyses by now. With spatial resolutions, we get statements, for example, reading along the lines of microclimatic processes affecting really broad-scale ecological processes. Think of divergent evolution, for example. On the other hand, we've got the temporal resolution, where we know that extreme events increase in frequency and in intensity as climate change proceeds. And then we get statements that tell us that more accurate variability and extreme event statistics, meaning capturing these climate extreme events on higher temporal resolutions with higher frequency and intensity, could give us some better performing models. Now, on the other hand, once we've got these highly resolved climate data sets of spatial resolution as well as temporal resolution, we still need a lot of different informations just to explain what's happening in biological systems. So with this, so far, we have largely relied in the past few decades on just air temperature and precipitation data. And I'm not even saying there's anything wrong with these two. While I do have my personal gripes with precipitation data itself and the downscaling thereof, I'm just not trusting it. I'm going to show you in a second here why I say this. I will say that we know that moisture and temperature are some very important variables when we want to understand or predict anything in macroecology. Now, as Richard already mentioned, there is a set of ECVs, the essential climate variables, which is, and correct me if I'm wrong here, Richard, 86 if I'm not mistaken, from which we can calculate a lot more in terms of variables, such as, for example, the bioclimatic variables you might be used to from use of WorldClim. All of these can be calculated with rather easy access from these ECVs. So we do not lose any of these variables when we make a transition from gridded observation data sets to climate analyses. Now, just with me saying I don't trust precipitation in particular, if we look at this precipitation climatology, just ripped right from WorldClim across a rather unsampled area in North America, we see that a few topographic features which we intuitively know should have an effect on precipitation, such as, for example, the Denali range, which should come in somewhere here, just doesn't show up our precipitation records. And if you look at where our station data actually comes from for these gridded observations, it becomes quite apparent why we have these very smoothed out patterns here that we could not improve on largely with ERA 5 if we wanted to, or ERA 5 land, just by virtue of how difficult it is to downscale precipitation by itself. So this means with these gridded observations, depending, of course, on where you are on the Earth and which climate parameter you're looking at, there are some areas where we have really low data reliability in these gridded observation data sets, with no way of telling how certain we should be of these data points. That's where I want to take a step back. And now that we've talked about the spatial resolution and spatial patterns in those gridded observation data sets, quickly just want to highlight how utterly important, to me at least, temporal resolution is. Because as we know, climate models predict that we have a consistent increase for the next few decades to come of year-to-year variance and intensity of that variance and frequency of extreme events in any kind of climate parameter. That is precipitation, that is temperature, that is droughts, so a drought index, for example. If we do not account for that temporal variability, we have a really hard time understanding how exposed our study settings are to extreme conditions. And with permission of Connors, who I think is actually joining us today, thank you again for this, mate. We look at this in a timeline, for example, of, in this case, midge abundances. Now, the underlying black line here shows us the actual population trends, whereas the red dots and lines there in between show us where we have sampled. And you can already see that if we don't sample often enough, So for example, with monthly samples, as we could obtain from gridded observation data sets such as WorldClim or KrigR, we would be left with some very relevant biological gaps that we just don't have data for. Now, this also leads to us not being able to correctly identify extreme events, such as a rapid growth or rapid decline, and the climate parameters coinciding with these events. When we then look at how complex our datasets need to be, when we look at the ECVs we get from legacy datasets, such as gridded observations like WorldClim or KrigR, we get from WorldClim, which is one of the bigger ones, roughly 26 variables, where most of these are the raw data or derivatives of air temperature and precipitation. Whereas on the other hand, with ERA5 and ERA5 land, which are the ones that we're targeting in KrigR specifically, we get around 83 variables, which cover all of the ECVs, which are out there that index important components of ecosystems and their potential interactions with the abiotic world, ranging from the atmosphere all the way down to soil properties such as soil moisture or soil temperature. The shortcoming that I'm seeing in gridded observations is further confounded when we look at the fact that data in these gridded observations is rarely available at higher temporal resolutions than monthly intervals, whereas with climate reanalyses such as ERA5 and ERA5 land, we get hourly intervals of data records, which lets us identify extreme events and trends in certain climatic variables just so much better. If we should downscale at hourly resolutions is a different matter altogether. Like Richard said earlier, for soil moisture, an hourly downscaling probably isn't the best idea, but we could still go for monthly downscaling and match the already existing temporal resolution, if not outdo it with a few other climate parameters such as temperature. Now, the last of me, at least for now, ragging on these legacy data sets comes in the interpolation method used, because all of these are at their core interpolated data sets between weather stations. This is problematic with certain ECVs, as we've already shown with precipitation, and a few others as well, which then build off of precipitation, for example. So the same can be said for drought indices. And the interpolation methods are usually not made publicly available, so they are not up for scrutiny. On the other hand, we've got the ERA5 and ERA5 land reanalyses datasets, which are derived from dynamic models instead of straight interpolations. They are thus a good fit to nature because of data assimilation practices, and the models are fully disclosed, meaning they evolve at a rather rapid pace, making sure we stay up to date with what is best practice in climate science. With this, we are ready to step into the actual KrigR package, because KrigR is a package all revolving around making climate reanalyses available to you in R and then some. To step into this, you can think of KrigR as your pal to get you all of the climate reanalysis data you want, but then manipulate the data some more so that it really fits your specific study need. So to obtain data through KrigR, first of all, you need a CDS account and an API key, which can be generated behind this link which I have already copied into my clipboard. You can find right there in the Zoom chat right now. I would like to ask you not to daddle around on that website right now, but we'll have a short break before we go into the R practical later on today. And this is where you might, if you want to follow along on your machines at the same time as I'm doing something, might want to have already created that CDS account and API key. If you don't, that is totally fine. Everything I will be showing in the R exercise later will also be up as an R Markdown file with an accompanying HTML file, which you can all find on our GitHub at the latest by tonight. So if you can't manage something today, do not worry. All of this will be accessible later, and we are recording this session. And then if no one of you interjects here, make that available too for anyone who wants to re-listen to it. That setting aside, we've got our download prerequisites. So the next thing we do is we move into the ECMWF-R package, which already exists for the R environment, where I just had to click into PowerPoint here. where we can already get Era 5 and Era 5 land data downloaded from the climate data store, the CDS, run by the ECMWF, who are the makers of Era 5 and Era 5 land. On the right-hand side, you can see a download list specification that you could then feed to the functions within ECMWFR. To my mind, this is rather unintuitive as a download specification, and there is no processing of any data. So what we've done in the KrigR package is write a wrapper function for the ECMWFR package to get to a more intuitive specification, at least to my mind, for your downloads. On the right-hand side, you can see that function call, which gives you the exact same data as this would give you. We have also implemented a masking according to shapefiles. You can see this on the right-hand side. The ECMWFR package only lets you limit your geospatial region by an extent bounding box, so a rectangular shape, whereas we can limit it according to a shapefile you put in to really decrease the size of files that you will have on your hard drive by the end of the download. In addition to this, we have also implemented a tiny functionality you can see on the right-hand side, which has not been included in the ECMWFR package, where we can already, in the download itself, aggregate the data you're pulling down to desired temporal resolutions. So we can make extra sure that it matches up with whatever biological data you are working with. More on this when we get to the actual practical. This is the kind of data we pull down. So right here, we've got surface air temperature for the 1st to 6th of February 2020, for example. And this has been downloaded using this function call right there. So now we have this data, we've got beautiful temporal resolutions. However, our spatial resolution is still on, if we use Era 5 land, for example, roughly a 9 by 9 kilometer grid. This is not quite as good as the WorldClim grid, even though I would say that Era 5 land already gives us more reliable data than WorldClim. However, we still want to match that beautiful 1 by 1 kilometer resolution. And for this, we use, as Richard already said, KrigR as a statistical downscaling method. For this, we need covariates at training and target resolution. And I noticed a few questions popping up, which I waved away earlier. Here's where the answers come in. For the KrigR itself, we use the KrigR functionality offered to us in R by the AutoMap package. And our KrigR package then provides us with a default set of covariates. For this, we use the USGS GMTED 2010 digital elevation model dataset, which comes at a slightly sub 1 by 1 kilometer resolution. So I think it's 980 something meters by 980 something meters for the entire globe as our default data set. This is downloaded and pre-processed to fit your specific needs using the download DEM function, which you can tell which data to match in the train raster, and then which resolution to put out to, or which raster output to match. Again, more on that in the R practical. Again, with a potential limitation by shapefile and a few other bits and bobs here and there, which I'll explain as we get to the actual exercise. Once we've got our covariates, we can then execute a third step in our KrigR workflow, which is the actual KrigR and an AutoMap wrapper from the package I mentioned earlier. Here we have changed how AutoMap works to a certain degree by allowing for parallel processing of multi-layer rasters, meaning if you have a machine or a server which has an abundance of computational cores, you can now make use of all of these in terms of multi-layer KrigR, instead of just letting everything run on just one core, meaning you can potentially increase the KrigR speed of a multi-layer raster by however many cores you have. We have also added in a few sanity checks before the actual KrigR starts to catch some of the most commonly encountered warnings or errors that one might face, and also to give novices in KrigR and statistical interpolation methods more understandable error messages instead of just the very cryptic R messages that everyone in here is used to by now, I assume. We, in addition to this, export the kriging uncertainty. Richard already highlighted that this is something we do, and to my mind, this is something that you cannot get from any other climate dataset or any other interpolation method that is currently out there. And since we have a lot of people from the Glasgow group with Jason here, on a more Bayesian level, a thing I have wanted to try for quite a while, but just haven't gotten around to yet, is using the ensemble uncertainty that we get from the reanalyses themselves, combine these with our downscaling uncertainties and see how these would fare as, for example, priors in Bayesian analyses, because I think they could be quite informative. I just haven't gotten around to it yet. And if someone snubs me on this, I now have this recorded. So this is the kind of data we get by the end of this, which is rather beautiful to look at and matches that GMDED 2010 digital elevation model resolution. Meaning right here, we've got roughly 1 by 1 kilometer of downscaled surface air temperature across Scotland for the first 6 days of February this year. Now, moving on from this, just to highlight how this workflow is structured, there are 3 distinct steps. The first one sees us obtaining the climate data by using our download error function. Next one, once we have this nice data here, is to get the covariates on training and target resolution using the download DEM function, which then gives us the elevation like this. Now, just off the bat right here, these covariates won't work very well for all of the ECVs in the ERA5 or ERA5 land dataset, and more on this in a second. Third step then sees us combining the initially downloaded climate reanalysis data with the different covariates to get to a downscaled product and a downscaling standard error, which then looks like this. We have the downscaled product on the left, and on the right-hand side, we've got the downscaling error. If I may just direct you towards the different color bars here, you can see that we have quite a big range on our actual surface air temperature and not a very big range on our uncertainty or standard error of our predictions for surface air temperature, which makes me very happy. But also you can see how these edge effects of the different shapefiles really come into play at the different boundary zones around the shorelines here. This is just something to be aware of, and if you need highly certain downscalings right around coastlines, it might be useful not to use a shapefile, but just draw very tight rectangular bounding boxes alongside your shorelines. With this being said, all of this works out the box, but sometimes elevation isn't the best covariate to use. Sometimes you may not want to KrigR ERA5 or ERA5 land. And in these cases, we have scripted the KrigR package in such a way that at any of these 3 steps, you can just input your own data. You do not need to create covariates for an ERA5 land data set here. You can use any data set you want and obtain these elevation covariates for it using the download DEM function. You can also use different covariates here and Krig an ERA5 or ERA5 land dataset with it, because the kriging function that we have is not particular to any of these or checks for whether this is an ERA5 family product and whether you are using a DEM. So you can use any kind of combination that you want of datasets and still get that multi-core kriging, still get that uncertainty. Now, if you don't want to have that level of control, or you just don't need it because you think for your application, what we're delivering out the box is enough for you, there's an even easier way of running these analyses. And that's the KrigR pipeline. Because our KrigR function either takes the arguments you have seen so far on screen, or it takes some additional arguments that specify what data to pull. So if you don't feed the KrigR function an actual raster data set, which it is then set to downscale, you can just give it a download specification and it will automatically retrieve the data, retrieve the covariates for it, and greet you with your downscaled product. All of this happens in one step, so you do not need to worry about it. It might just take a while because it needs to query downloads and then do some actual kriging. With this in mind, as a quick recap of how to use KrigR and what it does, KrigR has this three-step process of first downloading ERA5 or ERA5 land data. It also downloads UERA data. That is that very fine resolution European reanalysis dataset. I haven't highlighted this so far because it comes in non-square cells, which you can't KrigR. That's why I haven't highlighted it so far, but it is there to be downloaded if you want it. Our downloading automatically breaks the download requests into sizable chunks, so you don't get an error message from the ECMWFR package or the CDS service telling you that whatever you're querying is too much for them to give you. It aggregates hourly or monthly data to user-specified temporal resolution. So if you want daily aggregates, for example, you just need to specify this. We will automatically pull down hourly data, which will automatically be aggregated to daily data. And if you specified that you want bi-daily data, for example, those days will then further be summed up. The same happens if you specify annual means, for example, where we will automatically download monthly data instead of hourly data to make the download a bit faster and easier on your hard drive and on the computation of the aggregation by the end, where we then just build the mean of 12 months for the year. We can also mask the data that we're downloading according to a shapefile. The second step is then to get your covariates, where we provide you out the box with the GMTD 2010 data. However, this is being downloaded whenever you need it, so installing the KrigR package itself is relatively easy on your download and your disk space because we do not ship the actual data, just the download function. The KrigRing of the climate data is then the final step in our pipeline or our workflow, where we check for common errors, we have the parallelized processing of the multibands, and we can export the KrigRing uncertainty. What we don't do with the KrigR package is variable selection. So you still need to identify which covariates work best for which kind of climate parameters. You can consult the literature for this. You can run some trials as well on KrigR itself. It does not check whether these are sensible. This is all up to you to see and inspect how your downscaled products look. If you have large regions, KrigRing becomes absurdly expensive in terms of computational cost, and we do not automatically break these down into smaller regions for some local KrigRing and then fusing, which would speed up this kind of process tremendously. This is actually a process that we have coded ourselves for our global downscaling methods, because a global KrigR in one step takes months, if it even finishes at all. Whereas if you break it down into smaller tiles, which you KrigR individually and then fuse back together by the end of it, takes just about 8 hours. Finally, the KrigR data is not limited to realistic values, but only these statistically sensible ones. Meaning you may just end up, if you have weirdly specified covariates with, for example, temperature in a range of below 0 Kelvin, which doesn't make any sense and shouldn't happen frequently. But if these so-called lapse rates go absolutely bonkers because of either your choice of study region or your choice of covariates and what kind of data you have for these in these regions, you may want to check for just not realistic values in your final outputs. A few more things I want to highlight on our package with which you can make the most out of using it. The first one are just some quality of life improvements that we have found incredibly helpful as we have used it for a few studies by now. The first one is that the KrigR function leaks temporary files to your hard drive, meaning in a temporary directory within your directory that is indicated by the dir argument in the KrigR function. This is where all of your KrigRing takes place and where your output is going to be saved. We create a temporary directory, which is, if you have specified it as such, removed once the KrigRing is done. where we save the individual netcdf files for the KrigR prediction and the standard error or uncertainty of the KrigR prediction for each layer in the input data. So if we have an 8-layer raster, for example, this temporary directory will, by the end of it, hold 16 netcdfs. 2 for each layer, 1 prediction, 1 standard error. These are automatically removed, like I already said, once the KrigR is done and the final data set is saved to your directory indicated by the dir argument. The reason we do this is because with this, you can put a hold on KrigR, meaning if a server has to restart, if you're running this on your own laptop, but you need to catch the next bus, you do not lose the progress that KrigR has done over multiple layers so far. At most, you lose any kind of progress that KrigR has achieved on one individual layer, or if you have parallelized computing, a few individual layers, but never the entire data set. Because KrigR is run in such a way that it checks for the presence of the temporary files belonging to this function call, and if they are present, skips and loads them so it doesn't have to do the actual KrigR on these files. In addition to this, we have call tracking of KrigR, which is exported back to you as a third list element in the output of KrigR, with the first 2 list elements being the prediction raster and the uncertainty raster. We have kept them split from each other, so you don't have largely differing values from one layer to the next. This call tracking information contains which KrigR arguments were specified in the function call to KrigR, but also the extent and coordinated reference system, as well as the dimensions, meaning resolution, cell count, n row, n column, for example, and the layer names in your input data, meaning the data to be KrigR'd, as well as your training and target covariates. We do this in such a way that the call itself doesn't store the input data, it just stores however we would summarize these data, meaning it's very lightweight on your RAM, for example. In addition to this, if you want to make the most out of using KrigR, and I hope you will, here are some considerations to go with this. First of all, you have to consider the covariates we use. And I know we've been beating you over the head with this by now, and we will get to this a tiny bit more in the R exercise, which is to follow in just a second here. First of all, there is consistency, meaning we have to make sure that the relationship of our target variable, which we want to downscale, and the covariates of our choice to downscale with are consistent across spatial and temporal scales that we are interested in. Otherwise, the result will be nonsense. The download will still work fine, but the actual KrigR won't be the best. In addition to this, if we have collinearity in our different variables, we can exploit these relationships by co-KrigR, something that Richard mentioned earlier. If we have already KrigR'd surface air temperature, for example, which is very easy to KrigR, we could then use this as a covariate itself to KrigR something that is much more difficult to KrigR using just elevation, for example, like humidity. Meaning, as a take-home message from this, not all climate variables can or should be downscaled in the same way. As far as computational cost is concerned, as another consideration, the processing time scales close to exponentially with the extent and downscaling factor that we're interested in, as we've already seen with the Nmax example that Richard showed earlier. And adding covariates, on the other hand, only marginally increases the computational cost. So my recommendation here would be to downscale small regional products and then fusing them into bigger ones if you need bigger ones, using many covariates. Whereas on the other hand, with global and large region KrigR, which comes into this, it is important to know that some relationships break down between the hemispheres, meaning relationships between target variables and covariates. And the computational cost itself of doing a global KrigR basically prohibits us from doing it at all. So the takeaway from this, as I've already mentioned a few times, if you want to do large region or even global KrigR, you should do this in latitude bands or smaller tiles, break it down, KrigR it individually, and then fuse it back together in the end. So to round this all up, what we gained here is an R integrated access to some state-of-the-art climate products, the best we just have right now. A complete workflow for advanced statistical downscaling of spatial products within R, all in just one package. We are planning to expand on this a bit more by applying the KrigR methodology for climate projections and then deliver these as data products. We don't quite know where to host them yet, but we're quite certain it will be with some Norwegian institutes. This is still to come, and we are very much in the beginning phases of this. Just to go into what Richard said earlier of where you can get climate projections, we hope that in the near future we can direct you to a repository where we have downscaled climate projection data ready for you to download, so you don't have to go through wget or some other point-and-click adventure, which is then also going to be linked to what we've already done in KrigR, so you can get our tool and the data all from us, and it will be consistent between them. We also have an intercomparison study, which we are already working on, to look at how the different settings in KrigR work, how this works in comparison to some gridded observation data sets. As a spoiler so far, and as you may have guessed from what I've said so far, KrigR seems to be faring rather quite well. We're also working on a species distribution model in comparison to show you what it does when we look at climatologies. And we already have an application of KrigR and its use for vegetation dynamic studies, where the temporal resolution comes in a bit more, submitted for publication, but haven't heard back from them yet. With this, I am about to head into the R exercise. I see that I've gotten one question on the chat over here. And the question is about edge effects if we work tile by tile. That was one of my biggest concerns when we went into tiling the globe up to run local KrigS and then fuse them. However, the mosaic function from the raster package does a tremendous job of removing any kind of edge effects, because we have a slight overlay between the different tiles, and so we can get rid of any sharp boundaries. And as a matter of fact, the climatology, or not climatology, sorry, the global, well, yes, it was a climatology, but the global surface air temperature that Richard showed earlier was in fact a product of this tiling approach, and there weren't any edge effects in that one either. It does show up a tiny bit more in the uncertainty. So if there are no more questions, I am just going to switch over to R. And yes, good point. Another question, if I could say something about the limits to downscaling. That is a very good point. I'm actually surprised I didn't say that myself, because one of the first things I learned when I put this package out for the first time is that people are going to use it, but also misuse it. And this comes down very much to how far you downscale, because any kind of statistical downscaling should, as a rule of thumb, not be used for more than a gain in one order of magnitude as far as the target resolution is concerned. So if you start with Era 5 land on a 9 by 9 kilometer resolution, it is usually best to avoid any kind of target resolution smaller than 900 by 900 meters. In addition to that, you need to make sure that your covariates at the target resolution actually manage to be accurate themselves. We have another question from Fergus. I may have missed this. You talked about co-KrigGing, where you KrigR a variable and then pass it into the model of another target variable. Is this only computationally preferable to interpolating multiple target variables in the same model, especially if they're correlated? So the way this model works, unfortunately, it cannot predict multiple target variables at the same time. You really have to go through variable by variable. And the reason we would do that co-KrigGing is, you can think of this somewhat in a sense of a pyramid scheme, where on top of it, we have that one building block, the shiny pyramid tip that we want to get to, but we don't have the ground layer that could support it. So our terrestrial covariates, such as DEMs and soil parameters, wouldn't do a good job of, for example, explaining humidity in the air. However, we can get to that by adding in a few building blocks in between and using our baseline of soil properties and DEMs to get us to high resolution air temperature data, for example, and other kind of derivatives, to then get to a KrigIng of humidity, which would be informed by, for example, still elevation, but also the air temperature itself, which is a huge influence on humidity, but is that much easier to downscale than humidity itself. Yes, the order in which you KrigR, if you do, so sorry, there's another question here in the chat, which says, I'm guessing the order of KrigIng will matter a lot then. If you plan to do co-KrigIng, yes, it does, absolutely. So if you were to downscale, if we stick with this example, humidity, and then you were to try to infer air temperature from humidity, the results would be far, far less accurate than if you did it the other way around. If there are no other questions, I'm just going to keep an eye out for this. There is another one. What do we do about propagating uncertainty if we use downscaled covariates as covariates to downscale another variable? Is that quantified? Unfortunately, that's a really good point. Unfortunately, that is not in there, as we only track the uncertainty for each individual KrigR. What I would recommend you could try in that case would be to store the uncertainty of, in this example, the air temperature KrigR, then do your co-KrigIng using air temperature to KrigR humidity, and then take the KrigIng of that process and sum them both up. That is how I would approach these. But that also comes down to how you think about uncertainty. For me, this would be added uncertainty. Definitely something to be aware of as one uses co-KrigIng. All right, and I could just see there was another thing that popped up in the chat. Lovely. I will then just switch over to R, and you should all be seeing my R window right now. Is that true? Could I just get a quick thumbs up as a reaction or something? Lovely, thank you. Thanks for the feedback here. All right, I'm quickly going to have some tea because I just see it sitting next to me. And that has already gotten cold. The font bigger, absolutely. I will just, sorry, that is in appearance, isn't it? Let's go for a smooth 16. That font size look adequate to everyone? Lovely. Cool. Seeing a few thumbs up. Okay, there we go. So the first thing I do here when I start a KrigR project is, of course, and I should have already put that into my script, I just quickly, oh, come on, autocomplete. I just quickly empty everything I already have. Oh yeah, list equals ls. Well, that's getting off to a good start. I then start with a few preamble things. So the first thing I do here is I load some personal settings. These personal settings include my personalized API key and API user number, which I do not intend to share with anyone else or with the recording. This is why I don't put them in as strings into my document right here, but have them in an auxiliary file. I then also load some plotting functions, which I have defined beforehand. These I have made just for the workshop we're running through today. I do not plan on shipping these with KrigR anytime soon, because we would surely run into any issues as soon as someone has a layer count of 400 or something. So now that we're armed with this, if I needed to install KrigR, I would use the dev tools to install it from my GitHub. For this to work, I have found that on my machine and any other machine I tried this on, I needed to tell R to not use, not convert warnings in the dev tools functionality into errors. Because if we did that, even just a minute warning in all of the dependencies or the installation of KrigR itself would give you an error stopping the installation. And some of these warnings can be as benign as saying, this package was built on the version this and that of R, which does not influence how well the package works at all, but can still throw you an error message here, which is why that line 13 was very important for me. So moving on from this, I now load KrigR itself. I load a few additional packages here. Yes, just popped up in the chat right here. If I could share the example script, you will find, let me quickly navigate to this so I can put the link to this in the chat. You can find an HTML version with all of the outputs and a bit more explanation, which I plan to do just like this right now on my GitHub. Let me just quickly open the actual HTML file while I'm stalling a bit. And with this, here is the link to where you can obtain the HTML file that goes with this. And right in there, you have got all of those plotting functions that I've just loaded in like this on the side. They are defined in there as well, so you can make full use of this. The only thing this is missing is a definition of the API user number and the API key, which I have not hard baked into that HTML file. So moving on from this, we now can install and or load some packages with another user-defined function here, which just checks if the package is already installed. And if it is, it just loads it. If it isn't installed, it then installs it and loads it, which I find to be a bit more reproducible if I give my stuff to other people and just say library, and then they need to work out the kinks of which libraries aren't there. The packages I load here are just there for some further visualization and for some more third-party data, which we will get to in a few later stages here. We then just load all of these. Once they are loaded, we see that everything worked fine here. Now I'm indexing a few directories. This all comes down to how one thinks about code. Me personally, I have a very compartmentalized way of thinking about any kind of project I'm in. So I have folder structures which probably rival the evolutionary tree at this point. And I'm not necessarily proud of this because it can become a bit difficult. However, what I do here is I go through this, I read out my directory that I'm currently in, which is the directory for our workshop right now. I then append a data directory and a shape directory. I create these directories if needed, so if they don't already exist. Once I've done this, I then check if I already have a certain shapefile mask there. You will see that the HTML document gives you 3 sets of shapefiles that I have found to be exceedingly useful for any kind of biogeographical analysis, but especially when wanting to limit study regions in KrigR. However, I don't want to download this every single time, so here I'm just checking if it's already there. I already downloaded this ahead of time. If we take a quick gander into this folder, we now have a data folder. In here, we already have a few more folders, which we will establish in just a second. However, in our shapes folder right here, we already have the state mask of zip downloaded and extracted, which is just what I'm checking there. All of these shape files, with the exception for biogeographical regions, I'm obtaining from naturalerthdata.com, which I have found to be insanely helpful in getting any kind of shape files that are on a global coverage. So once I've done this, I load it in. I could then plot the entire thing. That would take a hot second, and I think we all know how the countries on the Earth look. So I am just going to go straight into our first example. With our first example, I will do the most basic function call that we can do to KrigR. So I will do the 3 steps, and I will not inform this with a shapefile, but rather just with a rectangular bounding box. This, I set an extent. This is a rough extent drawn around my home state in Germany, because that is an area I'm very confident in saying something about the validity of our findings for. And so as soon as the state mask has actually been loaded. It's unfortunately a rather large object, and I hope it will finish anytime soon so I can stop stalling over here. I can then show you a map of what we're actually looking at. And there we go. We've defined the extent. We now just get a Google map for this. As soon as this one's downloaded, we will plot this using the ggplot engine or the ggmap engine, which follows ggplot in the background. And this is that home state. You can see this outline right here, which is the German border to the Czech Republic in the southeast right here, and then Poland all the way in the east, and then a rather small outline border right here, which is just the state border within Germany. So even though I'm interested in the state of Saxony, which this is itself, I have not used a shapefile, and I'm just running with the extent. And now we'll look at what this does to our analyses. So what we do next then is, just because I think in folders, I create another directory, and I create it. It tells me this already exists because I have run this code beforehand to make sure all of this works, of course. So our next step is then to step into KrigR. And this is where I now call the download error function. I tell it to download surface air temperature, which is the 2-meter temperature, 2 meters above ground. I tell it to download from the ERA5 land dataset. I want this for T's in steps of 1, so that is T resolution, T step 1, for 1995, January 2nd to January 4th. The reason I've chosen this is just because it's snug right around my birthday on the 3rd of January, and I wanted to know what my parents had to get through on their drive to the hospital. So then I tell it about the extent that we're interested in for this study. I tell it where to store the data with the dir argument, and I feed it my API user number and my API key. When we execute this, it will say everything is recognized, and unfortunately, I totally neglected that it's now showing you my API user number and key. Please don't steal that. And we've already downloaded the data. This is how quick this can be for tiny data sets, for small time periods, using an extent. We can now plot these using the predefined plot function. And what we get from this, if I just draw this out a tiny bit again, or actually, just let me pop it out, why don't we? That may make it a bit more legible. Right here, you can see the square extent. We can already see some of the geographical features show up here. With the, it's called Erzgebirge. It's a mountain range on the border to the Czech Republic. Beautiful place, especially in Christmas time. It is very lovely. They make amazing sweets and have very beautiful traditional art down there. But I'm getting sidetracked. What I can already see from this is that apparently the day after my birthday, Saxony got cold, and I really hope there's no causality here. So moving on from this, we have our raw data. We could now look at the raster itself, but I will forego this, as you can find this kind of stuff in our HTML guide file. What we will do instead is obtain some covariates to do some downscaling with. So for this, I call the download DEM function. The download DEM function is now informed by the raster object that we want to downscale, so we can make sure that our covariates on training resolution match this, covariates in this case being DEM, hence the function name. Tell it to downscale to a resolution of around 0.02, which if we look at the resolution of our raster that we start from, is at 0.1 when we start. That's just the base ERA5 land resolution. Earlier, you might recall that I said you need square cells to do any kind of downscaling. You can see that technically this is not completely square. The KrigR function is thankfully able to brush aside these tiny, tiny differences in resolution. However, if you really have non-square cells, then it becomes an issue. We again tell it where to store the data. We tell it to keep temporary files. Keep temporary files in this case means it keeps the global download of the DEM. And what's happening behind the scenes here is right now it checks if the DEM is already in place and then doesn't download it if it's already there. Hence why I set keep temporary to true, so it wouldn't download the DEM every time. It now loads in the DEM if it doesn't have to download it. If it needs to download it, it will first download it, unpack it, then load it in. It will then limit it to the study region that you're interested in and resample the raster to match the different outputs that you want. So it will be resampled to match your input. So you have the exact same extent, the exact same location of cells, the exact same size of cells. If you give it a target resolution, it will try to get the output, so the target covariates, to the exact same extent as your input by aggregating the DEM to fit that 0.02 resolution in our case as closely as possible. Having done this, we can take a look at what we received from this, which is list. The list itself, that's weird. I should have probably not moved that plotting window while it was plotting. So I'll just do this again. But that also means I have to load the state mask again. All right, bear with me here for just 1 second. Maybe you've got some questions in the meantime. And if that is not the case, I will just have to stall again for a bit. All right, yes, of course. I have just been asked in the chat privately to repeat the last step because I lost someone on the resolutions of target and covariate. So the target itself right here is that state raw raster. That is what we downloaded in line 60. This always comes at the resolution that is specified by the ECMWF for the dataset that we're targeting. So if it's ERA5 land, we have a resolution of around 0.1 by 0.1 degree grids in this case. Putting this into the train RAS argument tells us that the covariate that we have, which is a DEM, will be resampled to match this. The DEM comes at a resolution of 0.0083 or 0.0086, which is a lot finer than our input data. So what we do is we aggregate a lot of cells together to get to a DEM that matches our input. I hope that makes sense so far. So now we have input data at that 0.1 resolution, and now we also have covariates, our training covariates, at that resolution. Now we still need our target covariates. And our target covariates we get by taking the superfine resolution DEM and aggregating the cells, because we don't have anything to resample to. So we aggregate these cells to get as close as possible to the specified resolution we set here. I realize that this is not what most people would want to use this for, because you want to use KrigR or any kind of downscale in such a way that it matches a pre-existing data set, I would wager to guess. And this is something we can do, and I will get to in maybe half an hour as we progress in this example here. I'm just starting as simple as can be, and then move to more real world applications. Now, thank you very much for that question. It was a beautiful time sync here. And now we've got our plots on the right-hand side. And just so this doesn't crash again, because unfortunately I have a rather weak laptop right in front of me, so I'm not doing too much with it right now. You can see that without popping it out, we again have these topographical features coming in with the Erzgebirge really coming in with some much higher elevations in the flatland northern Saxon area, which I'm from. So now we have got our covariates. We are ready as such to step into KrigR. And what we do here with KrigR, this is something you don't have to do, and I'm really just doing for the purpose of this workshop, is I am taking the time from when I start the KrigR function, and I'm taking time when it stops. So we can then look at how long this took to see what multi-core KrigR does, what using a shapefile does for the computational cost and time that you have to sink into doing these analyses. But to explain the function a bit more, What I first do is I tell it which data to KrigR. And in this case, that is our state raw raster. That's the 3-day period of surface air temperature across the extent box of Saxony. Our covariates, the coarse ones, so these are our training covariates, the first ones in that list produced by download DEM. So on the left-hand side, what I'm showing right here in the plotting pane. The right-hand side of that plotting pane goes in as covariates fine, or the target covariates. I tell it to not keep those temporary files I told you earlier about. I tell it to only KrigR using one core, so we can get some additional outputs that we've coded in here as a quality of life improvement. Tell it which file name to save this under, and we tell it where to save everything to. And with this, we are ready to run all of these lines together, just so I can make sure I get some accurate time assessments here. I run these at the same time. This might take a hot second, because KrigR by extent is rather computationally expensive if we are just interested in a certain shape, for example. And while this is running, I will just already prepare a tiny thing here, which, before we plot this, I am just pulling some stuff over, where we can then assess how long this took, this calculation of the time output, and then have a more in-depth look at what we produced, not just with plots, but also with the output of a summary of the different rasters. Now, one thing you can already see right here, which I'm doing on line 97, where I will be looking at the raster itself, is KrigR returns a list. This list in its first position holds a raster stack with all of your predictions. In the second position, holds a raster stack with all of your uncertainties associated with those predictions in the first list element and the raster stack therein. Whereas the third list element is the call track. What I explained earlier about saving the different dimensions, the different layer names, and such. Now you can see it just KrigR the first layer, and when we run this on a single core, we can do outputs to the console. So we've implemented an estimate function, which can give us a rough estimate of when this should finish KrigRing. So in about 1 minute, this should be done with all of the layers given the current computational resources that it can pull from. So I've got to stall for just about 40 more seconds, and this should be done. Back to the call tracking. If I were to just look at the entire list obtained in this state KrigR object, I would get an output for those two raster stacks in position 1 and 2, but then I would get a long list for the call tracking. And just for the sake of this workshop, and also for the sake of you wanting to just extract the data from this KrigRing list, you would just want to remove the third element. However, if I were you, I would want to store the call tracking alongside your objects on your hard drive, just so you can make sure where it came from. There's a question if 0.02 is the lowest resolution we can KrigR to using the DEM as a covariate. Someone has already tried 0.01 in the past, and it has given them an error saying you're trying to KrigR greater than 1 order of magnitude. That is not an error message, that's a warning message we've implemented. KrigRing goes ahead if you try to KrigR more than 1 order of magnitude. We still let you do it, we're just throwing you a warning message, just so you're aware that there might be something happening here. The reason why it does that at target resolution 0.01 is because your input data with the DEM is 0.0083 in resolution, and trying to aggregate 0.003 to 0.01 is unfortunately not possible. So it just keeps it as it is. And what it really does is it KrigRs down to 0.0083, which is more than 1 order of magnitude finer resolved than our input data was. So that's why you're getting this warning message when you use it that way. And the finest resolution we can KrigR to answer the first part of that question is the native resolution of DEM, which is 0.0083. And with this, it just finished. We can now look at what we actually get here, what we get is, sorry, not a raster stack, a raster brick that shows us our dimensions with our layers therein, different predictions that we have for each day with the extent. Everything just looks like a regular old raster for anyone who's used to seeing these. And so we can plot this. We have got the first downscaled product of the day, and some more are yet to follow. There you have it. On top, we got some beautifully downscaled air temperatures across this range of Saxony, where now the DEM data is insanely pronounced with the different elevation effects in our air temperature records, which makes perfect sense. And we can also see that, unfortunately, the day after I was born, apparently the weather or climate, or however you want to call it, became less predictable in Saxony. And now I'm really afraid that there's any causality, which I do not want to be true. And I don't think there is. But this is how we can interpret this. So this uncertainty here goes with this prediction here, this uncertainty here goes with this prediction, and so on. Now that we've done this, we could do the same thing using the pipeline. For now, I will hold off on using the pipeline because I could, although no, you know what? Let's keep this simple for now. And I will go with the pipeline, even though it will take a hot second to KrigR. And that's just going to be a tiny tea break. So we can also specify the KrigR function a different way than what we've done so far by not feeding it a raster data set. What we do here is we basically give it the exact same arguments as we would to the download error function. So we specify how to download, for what extent, for what API user, for what API key. Then we also give it all of the arguments we would give to the download DEM function, meaning what target are we downscaling to, how many cores do we want to use in the downscaling itself. So this is now a KrigR argument itself. We tell it what the final output should be called, and it should be stored. So with this, KrigR automatically recognizes I haven't been given any data. So I'm going to try and find a download specification within the other arguments I have been provided. I will then download, actually while I'm talking, I can just set this running. I will download the corresponding function, and I forgot to create the corresponding directory. That was a rookie mistake. So again, we just open up a new directory for this. And now it can run. So then KrigR downloads the specified data, error 5 land, aggregates it temporally. We then download the DEM for this, and we create the output, which was very fast, I have to say. Yeah. This was, oh yes, of course, sorry, I still have temporary files lying in that directory, so it just loaded those temporary files. So there's another question here, where is the DEM in that call? The DEM comes in by saying we have just downloaded data corresponding to this. We will now use this data as our, if you let me scroll up here, as our train raster. So that is what we resample to. So we automatically call the download DEM function if we haven't been provided with any covariates themselves. We will then use this already downloaded error or error 5 land data as our train RAS argument. We specify our target resolution right here as we would in the download DEM call. And the temporary automatically set to true, whereas the directory here is the same directory as here. And with this, we get everything in just one pipeline. So now if we plot this, it looks the exact same as what we've produced previously. And if we just have a quick look at the pipe KrigR predictions and the state KrigR predictions, so what we've done in 3 steps, are not the same. That is different. That is weird, because when I ran this previously, it worked. So I will have to investigate this somewhat further, because these two should be the absolute same. But instead of doing some troubleshooting right now, I will investigate some further and get back to you guys. Because what I want to get to is the more advanced use of KrigR. And what we get there is now we will work with a shapefile. So again, we extract the shapefile from that state mask we loaded earlier. We get our Google map for this. We plot that funny thing. When plotted, we can now see the outline that we're interested in. Again, we create, that should have all been in there. Let me just move this down so it's in the right location. We create a new directory, which again, I get a warning message because I've already created this ahead of time. And now I do download of error again in 3 steps, just to keep it simple for now. And so we can track the actual time it takes to do the KrigGing instead of the entire pipeline, where I do the exact same specification of the download of error 5 land data. Just this time, instead of specifying a rectangular bounding box, I am specifying a shapefile for my download. So I am querying the download. This again takes just a second to register with the CDS. Depending on how much traffic they've got going in and out, this can take a long time, especially if you query large data sets themselves. Now, if we plot this, we can see that we do not have the full extent of data anymore. What we do have is data masked to the shapefile, however, not masked as the raster package would do by default. By default, the raster package masking function would retain only those cells whose centroid falls within the bounding area of the shapefile. However, we wanted, when we coded this, to ensure that we, and by extension you, get exactly the data you want, meaning everything that even just slightly touches the shapefile has to be included in the data we pull down. So that's how we do the masking, as opposed to what you may be used to from the raster package. We do the same thing for download DEM, where again, we specify a 0.02 resolution. Tell you what, let's just actually do this as a 0.01 resolution for now, just so we can see that warning message that someone commented on earlier, where we do this while this is running. I will just set this up here running as well. So we've got the times to compare here in just a second. I forgot to do this earlier. So earlier we took 3.8 minutes to KrigR the entire thing when we were doing this by extent, with a downscaling down to 0.02 as a target resolution. Now, if we plot our new covariates and then have an actual look at the covariates, this is now the crux we get into when looking, and something seems to have gone wrong here with the resampling. So this is why it always pays to look at the different outputs. Because this pattern should be reversed. I do not know exactly what happened here. As you can see, what I was talking about earlier, it tries to aggregate. And, oh no, this is totally fine. Totally sorry. Yeah, I have 2 different color bars. See, I don't even know how my own plotting functions work anymore. Terribly sorry. I'm a bit scatterbrained today, it seems. But what you can see is download DEM attempts to aggregate to your target resolution because it doesn't have anything to resample to exactly match it. So if we specify a 0.01 resolution, we just get the unaltered DEM as our target covariate with a resolution of 0.0083, which is, as a matter of fact, more than 1 order of magnitude down from our starting point. And for this, we can now run the KrigR again, specified the exact same way as before, just different input data sets, and that shapefile, of course. When we run this, of course, might take a hot second here, because this time we are downscaling even further than just 0.02. And we will see what has happened here in terms of time for this. You can already tell this came up much faster than last time, even though we are downscaling to a much, much finer resolution than we did previously. And you can just see how it's taken along. So keep in mind that just previously we used 3.8 minutes to get from 0.1 resolution to 0.02 resolution. Whereas now we are going from 0.1 resolution to 0.0083 resolution. This only took about 32 seconds instead of 3.8 minutes. And this is to highlight how much of an improvement it could be for you or others to make use of this shapefile functionality that we have implemented into KrigR itself. You can see the results look just fine. They all fall neatly into this area of Saxony, which is done by the way we're doing the masking instead of that clipping by centroids. We can see that the uncertainties are still behaved very much the same way as earlier. We have this speckling that Richard touched on earlier in his initial lecture, where you can see that due to some edge effects, we now get this speckling, which really tells us that the local already existing data is used quite a lot for the prediction of these new cells there. So with this in mind, we have already improved our KrigR by quite a lot, just using shapefiles. Now, the next question would be if we could do this even better. And for this, we would turn to multi-core KrigR. So what we do here is in the same directory, we just run this KrigR again. However, this time, everything is still specified the exact same way, just this time we use the cores argument to tell it to use 3 cores. I could have told it to use as many cores as my machine has available. However, because we only have 3 layers, I didn't see any use in specifying more cores here. Now, this will take a while, and we will quickly look at what happened here in just a second by looking at how long it takes to KrigR using separate cores. We also plot this stuff, of course, when it's done. You can see it was done, and we get this warning message, which we also got previously, which someone mentioned in the chat earlier, where it says it is not recommended to use KrigR for statistical downscaling of more than 1 order of magnitude. You are currently attempting this, which means, yes, we specified a resolution of 0.01, but because aggregation can't be done from 0.0083 to 0.01, we are technically trying to get more than 1 order of magnitude out of this downscaling. And I would say this is just about fine. This is on the cusp of you shouldn't do it, but you would certainly mostly use this with pre-existing data sets, which comes up in just a few seconds here. So there's another question in the chat here, which I will get to in just 1 second, because I want to have a quick look at the time that this took. Interestingly enough, this was still a bit faster than the other process was. Now, earlier I said you can decrease your computation time or increase your computation speed, however you want to think about it, by the number of cores you use. So previously, it took us 37 seconds to KrigR this on just 1 core, and now it took us 25 seconds. That isn't a decrease of 1/3 or a decrease to 1/3. So the reason for this is because it takes the program a couple of seconds to even just open up those virtual clusters and cores to work on, which takes a bit of time away from you. If you use this parallel processing on multi-layer rasters, which have 400 different layers, for example, more or less course, as well, this reduction in processing time becomes that much larger. So now going over to the questions in the chat, Ewan asked, so if you're interested in a few points rather than the whole grid, presumably you should define shapefiles as buffers around your points. Can the package do that automatically? That is something I hadn't thought about that yet, actually, and that is something the package does not do automatically. The big problem with this that I could see happening if we had something like this would be if you have points which are, for example, on the shoreline, but you query Area 5 land data. If we automatically build a buffered shapefile around it, we couldn't use much of the area in the shapefile because it would fall on water areas, which Area 5 land doesn't have any data for to begin with. So we would try to downscale to a finer grid from which we can then extract point data by not having a lot of data to begin with in the first point. So at this point in time, it would be more useful if you had your own shapefiles for this. But yes, Ewan, absolutely, it is much better to use shapefiles which are buffered around points than to downscale an entire region only to obtain a number of points afterwards. I hope that was a satisfactory answer. And if you've got some nice ideas of how to make shapefiles where we make sure we have enough data to begin with for the downscaling, I am all up for making this package more useful. So the next question sent to me in private was, could we just double check on the units of the downscale DEM? It looked like the value range increased quite a lot. Is that possible? I might be wrong on this. So this is the units. With this, you mean the values, I'm sure. So the values of the native DEM that would be, which in our case is COVS LS2. Let's just look at that one in isolation. So what we got here is, and this is certainly an edge effect. For some reason, it is saying that we have, oh, sorry, no, I was looking at the IDs, which are totally fine. So this actually looks fine to me, and it might be something in my plotting function, which just has gone haywire, so I should probably double check that. Data itself is totally fine. A lowest elevation of 62 for the state of Saxony is very, very much in the realm of possibility. I think my parents' house just lies on about 80 meters of elevation. And the highest elevation should be the Fichtelberg, which is just around this elevation. Yeah, so this is really just a plot issue. Thank you for pointing this out, though. This all means that I can rework those functions and make a better HTML file, which will always be up on my GitHub. So as soon as I make some changes to this, as well as the package, it will come up there. Now, the next thing in making our KrigR a bit stronger still would be weighted local KrigR. And now I'm just going to stop tracking my different specifications of times here. I think I have proven the point quite clearly that the biggest improvement you can have is using a shapefile. And after that, if you just use a number of cores on a multi-layer raster, that's super useful too. So what I'm now interested in is showing you how this nmax parameter works. So this means how many of the original cells, meaning training resolution, do we take into account for predicting the downscaling of each individual fine resolution cell. And in this case, I have taken something very, very small in terms of radius that we're drawing, which is 15. And mind you, in the guide that is online, I'm doing all of this on a target resolution of 0.02. So I may be surprised by the results as well. So you can see how I interact with this very much live in this sense. So again, we KrigR this for the shape. Once this is done, we will plot it, and then we will have a look at the predictions and at the uncertainties. I can already tell you that the predictions won't change that much. However, the uncertainties will change quite a lot. And as you can see, the predictions have stayed very much the same. However, on our uncertainties, we can see how some other topographical features are now really stepping up to the plate as it comes to calculation of uncertainty. So for example, river valleys. such as this one down here, which is the valley of the river Elbe, which goes from the Czech Republic all the way through Dresden and then ends up near Hamburg into the North Sea. We can see this wide valley which flattens out a bit as we get to the flatter areas of Saxony itself, show up quite well. We can see the different areas here where there has been open pit mining during the last few decades, which has now been filled up with a bit of water areas and lakes and such, which really show up because they're extremely flat. And the same can be said in all of these other ones. Now, moving on from this, we can get into the aggregation of temporal steps. And I think instead of showing you much of this, I will just show you what I've got in the HTML file for this. We've got all of this good stuff, but then we get to the section on temporal aggregations. As I already mentioned, KrigR, or download error, automatically identifies which target data set to download from on which temporal resolution. So if you tell it to set or if you tell it to target hourly or daily data, so you set T resolution to hour or day, it will automatically pull hourly data. And in the case of daily requirements from your side, it will then, before doing anything else with it, take every 24-hour intervals and aggregate them into 1 day each. The same happens for annual stuff. So when you specify year as your T resolution, it will automatically pull monthly data and then aggregate 12 months together to fit 1 year. Now, what happens with this is that you can also specify temporal steps, meaning building on your temporal resolution, you can specify the steps within which you want to walk along that resolution. So if we want to have a 2-day aggregate, for example, we will specify T resolution to be day and T step to be 2. If we only call for 2 days and specify this, download error will download 48 individual layers, meaning 1 for each hour in those 2 days. It will then first aggregate all of them to 1 day each, because you have specified day in your T resolution, and will then aggregate them even further to be a 2-day interval. So you just get 1 layer out, even though download error downloaded 48 layers. And it does not keep these 48 layers unless you tell it to. There is one more thing on this, which I just implemented this morning. Jazz, who's on the call, told me it would be a good idea. And I actually have to agree, I couldn't quite believe I hadn't put that in yet. Because what I highlighted earlier was that you can get these extreme events from the data. And for this hourly resolution is really the highlight, I would say. Because even if it's an extreme event, you can still statistically downscale it in a spatial sense. But you want to have that extreme event record for the finest temporal resolution you can get it from. So whereas right up until this morning, KrigR automatically just downloaded and then aggregated to mean, you can now specify a range of different base functions of R, which can also be fed to the stack apply function of the raster package, such as min, max, or mean, for example. So if we had a download query, and unfortunately I haven't prepared any workshop material for this yet, so I'm just walking you through it like this. If we had our 2-day example from earlier, we would be interested in, for example, the minimum temperature achieved in this 2-day period. So what we then do is just add that argument of fun into our download error call or into our KrigR call, which targets the pipeline, which would then tell it, all right, we'll start here and we will download 48 layers. Out of those 48 layers for the first day, for those first 24, we will identify the minimum for each cell. We will do the same thing for the second day, And once we're done with both of those days and we have the minima for each cell for each day, we look for the minima for each cell between these 2 days. And with this, you can get to such a fine resolution extreme event by still aggregating long periods of time together. Now, the crux with this is if you're interested in the absolute minimum for a certain location in a year, you should not specify year as your output or as your T resolution, because then error or KrigR or download error will automatically target monthly data, and it will just give you the minimum of the monthly means, which is certainly not what you're after. So this is just something to keep in mind here. And to walk you through how you could specify different things to get to a desired output, if you want hourly intervals, you just specify hour to be your T resolution and then 1 to be your T step, or you don't have to specify it because 1 is the default. If you want 6-hour intervals, again, you set your T resolution to hour, but then tell it to have a 6 step. Same for 12-hour resolution, just change T step to 12. If you want daily intervals, that's day and 1. If you want weekly intervals, for example, that's day and 7. Month is the default on the T resolution, so you wouldn't have to specify it if you wanted something else than month. Another thing to keep in mind is that just by how this works with the data download itself, if you were to specify that you want to have the mean temperature for each cell in your specified study region for the month stretching from the 20th of January to the 20th of February, and you entered it like such. So you would say the 20th of January is my start date, the 20th of February is my end date, my temporal resolution is month, and my time step is 1. What our function will do, given how it's limited by how the ECMWFR package works, it will download monthly data for January and monthly data for February and give you those as outputs. Because you have some days in January and some days in February. And when you target the month, it will not recognize the days anymore. It will just say, okay, we've got some in January, we've got some in where did that came from? We've got some in February. Let's just get these individual ones, because it doesn't download the hourly data, it downloads the monthly data. I hope I'm not confusing anyone with this. So if you wanted the month stretching between the 20th of January and the 20th of February, you should run this as with those dates, but then tell it to have a temporal resolution of day, so it downloads the hourly data. Have this in steps of, for example, 30 to get to that month period between these 2 dates. Another important thing to recognize here is that we break down these individual downloads, so you don't query too much at each individual point in time, because otherwise it will either take exceedingly long to get that data set ready for you for download, or the CDS will go on complete strike and just say, I'm not giving you this because it's too big a data set. So what we do is for each month specified in your function call, whether you're targeting hour as a T resolution, day, month, or year, we always break it down by the month. We pull down data for that month, and then we move on to the next one and pull data down for that month. So if we still go with the example that we just had of the 20th of January to the 20th of February, which is 32 days in between the two, including start and end date, we could say we are interested in the full month as days. So we take our days, aggregate them to a 32-day period. This would result in 2 downloads being carried out and then fused for you. So you don't need to worry about it, just more of an explanation of how it works behind the scenes. On the other hand, if you would specify something like the same period, but instead of 32-day aggregates, you want 8-day aggregates, so you get 4 layers out by the end of it, you don't need to worry about any of this either, because again, it is 2 download calls, because we still only have 2 months that are somewhat touched on in our data retrieval. and you will receive 4 layers because the temporal aggregation is completely handled by KrigR, which I hope will make for a useful tool for you as end users, as well as me as an end user myself. I have found this quite helpful so far, because with this, I can make sure that my time steps of my climate data match with my biological input data 1-to-1. And then I can use the downscaling methodology to make sure they also match in the spatial resolution. So with this, stepping back into R, I just quickly need to find again where we were. We get into this very big important thing of matching something that already exists. And what I've done here might be a bit shocking because it's a lot of code that I'm throwing at you in just one instance like this. Basically, what I can explain away right here is I am now changing the shapefile we're interested in to be California, because I am now looking at much greater cell sizes, because right now we do not want to get to the highest resolution we can, but we want to match an existing data set. And for that existing data set, I have chosen an annual mean NDVI set for California. And the reason I've gone for NDVI is because that's what I'm familiar with. And the NDVI comes at a native resolution of 9 by 9 kilometers. Now, you could automatically recognize, well, ERA 5 land is on 9 by 9 kilometers. Why do we need to do any downscaling? And you would be totally right in thinking that. We might have to do some tiny resampling to scuffle around the edges of the squares just right so they match up, but we wouldn't have to do any downscaling itself. Just to show how this can work, however, I am now polling some ERA 5 data, which is a 30 by 30 kilometer resolution, and we are going to be downloading that and then downscaling that as well. So what we do here is we have created our reference raster, which is our NDVI values, which we want to match in terms of resolution, extent, and the likes, as well as coordinate reference system, of course. I'm doing this through the GIMS package, which is all of the code that is in here. So you don't need to worry about this. I assume that your biological data sets you want to match just already live on your hard drive at some point. So we've got that reference raster, which I created beforehand. Again, we've got a certain directory we're interested in. Of course, I pre-established this. Now we download ERA data for this, so ERA 5. Again, the function call is the exact same. However, this time we specify that we want ERA 5 data instead of ERA 5 land data. And instead of polling from 1995 and air temperature, we are now looking at air temperature for the entire year of 2000, which is where we obtained our NDVI data for. And we want this in a yearly resolution, so annual in a one step. If you specified something that it couldn't do, it would just give you the raw data without doing any temporal aggregation and throw you a warning message saying, I couldn't do 2 steps here, for example, I'm just giving you the raw data. Or if you specify a 2-day, let's say you specify a 2-monthly or bi-monthly aggregation, but you target 3 months. In that case, KrigR or download ERA will say you specified you wanted bi-monthly intervals. However, I found 3 months in your data. I am just giving you the first interval. So this is where it communicates with you to make you aware of what you've done isn't possible in the way you probably wanted it to be or how you mistyped it. But we're still doing however much we can on the end of KrigR to make sure you can at least run some preliminary analyses while you fix the other stuff. So what we do here, we call the entire pipeline, we've downloaded our stuff, we have already gotten our new state shapefile here. Again, we've got my user and my key number. We've got this time for our target res specification, not a resolution we're interested in, but the actual raster. And what this does is when the covariates are built to match what we need for the KrigR, instead of trying to aggregate from that 0.0083 resolution to whatever resolution you have specified, the covariate data will be resampled to match your target raster 1-to-1, meaning these are absolutely comparable, and you could do raster math with them afterwards because everything links up. So we just call the entire pipeline. Again, our download gets staged. I am just quickly going to make sure that a common issue I have run into here, I don't run into again. But I will, so I can just immediately stop this here. Terribly sorry. Because if you do repeat runs of this, you will already have the actual output in here, and it will unfortunately delete the output of it of itself, which I want to keep for some plotting. It is usually not a problem because you do not need the raw data after you're done. However, I want to keep it this time just so I can show a nice comparison plot of what we've done after the fact. So this is not a bug of KrigR. This is neither a feature of it. This is just something which, for workshop purposes, I have found tiny bit tedious. It should never be a problem in your actual workflow. So while this is running, you can see it stages each month individually. Like I already said, we break this down by month. So right now it stages January, February, March, and so on, and downloads for each of these just one layer because we have targeted months. So it just goes to era 5 and goes to the monthly product of era 5 and downloads that. Sorry, this is not COVID. This is just a dry throat after this much of talking. And while this is working, I think I'm actually going to replenish that. Are there any questions so far? I'm afraid that because of the lack of face cams, I cannot really read the room right now. So I hope everyone's still on board with this. Quick thumbs up or something. Just tell me if you're still following along. Coolio. Thank you very much. So now that we've got this output, this compiled completely like we wanted it to, I have now just copied over even more code right here. Don't worry about any of this. You can read all of this in the HTML workshop file that I've got uploaded and I sent you the link to earlier. This is simply just for visualization. Because now when we run this, and this time I will actually try to get into the plot here by zooming into it as soon as it's done, that is. I mean, it's telling me that it's done, but I don't really believe that. Oh no, it should be done. Okay. Let's see if that did anything. Well, it doesn't let me zoom in. Now it does something. There we go. For some reason, it just didn't show in the tiny pane. But here we go. So again, we can see that we have this fact that everything belonging to California, even just to the slightest margins, for example, this island right here, is included in the data set in both of them, both the input and the output. This is the NDVI raster that we wanted to match. You can see that we matched it 1-to-1 in our output right here, just not in terms of values. The values, of course, are different because it's 2 different parameters, but the resolution, the extent, the shape of it all is the exact same. So now we could use this to, for example, run a correlation analysis between the mean air temperature for the entire year of 2000 to explain the NDVI mean for the entire year of 2000. And alongside that, we also have our uncertainty, which again, due to a few edge effects, has these different spatial patterns here because these edge effects really nudge some high uncertainty into our range. And then these spatial effects of the different cells being downscaled spatially really comes into play. You can see this quite clearly in these island areas here, which have just a few cells to go off of in the original data set, and thus have a really high uncertainty alongside them. So this is not something you need to worry about this speckling. This speckling really just tells you that you have some cells where you have very high uncertainty. So for example, these data points where there's not a lot of data around it in the training set, you can see here there's really just this one cell, and then just a few, one cell away from that. So with this, we have matched a existing data set. Next thing to look at is the call tracking before we get to our last exercise for the day. With the call tracking, this is just to show you what is exported by it. Let me see if I can make this go without R crashing. I'm probably just being paranoid now because it did that earlier. You can see that we have a rather long list, which tells us what class our data was in, how many rows it had, how many columns it had, how many cells were in there, what the extent was, what the CRS of it was, the names of the different layers in there, if your layers were to index different days, for example, or different variables, if you wanted that. We then have the same for our coarse covariates. We have the same for our fine covariates. And we also have a few additional settings which have been provided to the KrigR function, either as a pipeline or as a three-step process, where we get our KrigR equation, which by default is error as a function of DEM, and more on that equation in just the next exercise. Also, what other messages we've given this, if we should keep temporary files, and how we retrieve the data, what type was it, wasn't a reanalysis, because this time we ran it as a pipeline. It stores how we wanted to obtain data alongside the specifics of how the data looked. So this really helps you keep track of how you created a certain object. I don't think I need to elaborate on this much more. So I am just going to move over to our last exercise. And for this one, I will be going back to Saxony. This time I am interested in soil properties. So what I am doing here is I am obtaining third-party stuff. And before I forget, I know it's in here, I just create, oh, sorry, seriously dry throat now. I will just take a quick second here. Going to be back with you in just 1 minute. Okay, let's see if that did it. So we've created a new directory. And in this directory, I am now checking if I already have thermal conductivity of saturated soil data set downloaded. If I don't, I'm going to just obtain it from globalchange.bnu.edu.cn, which leave it to, I think that should be the Canadians, to have this many dots in their web addresses. I already have downloaded this because I didn't want to have to wait and stall for time as this happens. So I am just loading this in. I then also load in my thermal conductivity for dry soil, so I have the full spectrum of thermal conductivity. And this time, I will be interested in not air temperature, but soil temperature. So what I'm doing here is I am querying the download of soil temperature at level 1. And at this point, you might ask yourself, where the hell are you getting all of these different variables from? For this, we have implemented a function called variable list in the KrigR package. And with this, you just need to specify which data set you're interested in so that we can tell you what variables are actually in there. In our case, we are interested in ERA 5 land. And right there, you get a super long list, which actually, why don't we put a view wrapper on this? And then we get this data frame, which is right here, what we call clear. It's just the full name of it, which you could probably read and know what it's about. This right here is the download column, which tells you which string to pass on to the download DEM function or the KrigR pipeline so that the download can be executed. The unit just tells you what unit this is measured in. So for example, with temperatures, all of this is measured in Kelvin, not in Celsius. And if you needed to look for how something's measured, that's where you would look for this. Another neat feature I just want to show you, if you're not quite sure how to write the data set into this, just do it like this. Sorry, because if you misspell this and you were to say look for error 6, we automatically have a function for this, or a warning message or error message rather back to you, which says you can look for error 5 and error 5 land. So these are the two data sets we recognize for this function. Now, moving away from this to our actual code, you can see that now we again want to look at my birth period right here, again days and so on, everything the same way as previously, but this time we are looking at soil temperature at level 1, which is soil temperature in the depth range of 0 to 7 centimeters. Another nice thing right here that a reanalysis dataset gives us is that we can get these soil properties in distinct depth layers, which is something we cannot get from gridded observation datasets out there because they just don't have it. So we can actually make some arguments based on how different depths of the soil might influence, for example, vegetation, depending on root sets. Again, we plot this. There it is, with a nice outline. Now we have to do a tiny bit more trickery to get our third-party covariates into this. This is what we're doing here. So the first thing we do is we crop this to the extent that we're interested in. Just to go along with this, just so you can see what this is. This is our thermal conductivity of saturated soil cropped down to the extent of Saxony. So now we take the shape file that we have, we rasterize it, get the cover from this. So this is how we do that masking. That doesn't only hold back centroid containing cells. So there's rasterizing might take a hot second here. When we plot this, we will get back, this is just for anyone in here who hasn't worked with the rasters as much yet. We now get this kind of plot, which shows us which cell is covered how well. You can see that there's a lot of zeros and a lot of ones, but they're right at the edges. A few cells which are only covered marginally by the shapefile. So now in this raster, we set every cell which has a clear value of 0, so isn't even clipped ever so slightly by the shapefile, to NA, which means we now get a plot that looks like this. We don't have any values in the surrounding area. We have kept all of the actual data, meaning even something that is just slightly above 0 is still in here because it's even just slightly clipped by the shapefile. We then use this to mask, and we then get our TK sat ras, which looks like this, and is beautifully cut just to Saxony, but includes all of the cells that even marginally fall into the shapefile. We'll repeat the same step for TK dry ras, and then we will just have a quick look at one of these. These are, of course, the exact same extents and resolutions because we've created them the same way and obtained them from the same data source. Now, when we look at these also have a resolution of 0.0083, so we could combine them with something obtained from download DEM. For sake of speed here, which I now realize I wouldn't even have needed that much, we can just run with this. So we now do the following. We do some resampling. So what we do is we stack our coarse covariates by resampling each one of these third-party data sets to our input data. That is exactly what happens in download DEM with the GMTD 2010 dataset. So now we've got the coarse covariates. We set names for these. So this is a raster stack. I want the first layer to be called TK wet and the next one to be called TK dry because one is wet, saturated soil, the other one is dry, unsaturated soil. This just makes it easier to have our raster specification, sorry, not our raster, our KrigR specification later on. For the fine covariates, we want to downscale straight to the target resolution here of whatever is the native resolution of our data sets. So we just stack these two. Again, we set the names. The names between these two need to match. Download DEM takes care of that. However, if KrigR can't find the same variables. The order is not even the issue here. They can be in whatever order you want, but if you don't have all of the variables you use for training in your target raster set for your covariates, you're going to run into an error message, and we cannot run the kriging. So now we just have this as a list, so we can use our plotting function on this, which we've created. And there we go. In data, target data, in data, target data. Now we can start our final KrigR for the day, where I show you that we can use, so this doesn't work in the pipeline. Obviously, we need to go into the individual steps to do this, like I explained earlier on my PowerPoint presentation. We still feed it the information of what to KrigR, with which covariates, and then how else to specify it. So again, here I'm just running this in parallel. Now on the KrigR equation, which we haven't used so far, because by default it just targets error data and your DEM. We now tell it to please calculate error as a function of dry thermal conductivity and wet thermal conductivity. We could also, if we had a DEM, write something like an interaction effect between TK dry and DEM, as well as TK wet, the DEM. This would absolutely work. Another thing to keep in mind here, or something that I find relatively useful, is if we don't specify this, and actually, why don't I just do it to show you instead of just talking about it? Now we've run this, and we get this message back from KrigR automatically, which says that none of the terms specified in your KrigR equation are present in the covariate dataset. The KrigR equation has been altered to include all available terms in a linear model. So we now have, by default, the package tries to get the most sensible linear additive model out of what you've got available. And it then says, okay, I can't do what you've told me to do, but what I can do is have the data be a product of TK wet plus TK dry, because these are present in both of your covariate data sets, which is the exact same as what we would have entered by hand. I would always recommend doing it by hand, of course, but this works too. So here we just say, yes, that's the right one. Please continue with that. And it does the KrigR for us. And then we have our final plot, which comes up in here in just a second. Well, as soon as it's done KrigR, which might take a hot second. I'm just already going to query the plot here. And in the meantime, here we go. So it again told us that it's not recommended to go down to lower than 1 magnitude, because we have a 0.0083 resolution. And there we've got our result. I am going to say that I don't think this is a particularly good KrigR, because our uncertainty is very high, ranging all the way from 0 to all the way to 0.5 Kelvin, apparently, on a native range of the predictions of just about 10 Kelvin. So this is about 20% of uncertainty on the actual prediction range. This is not to tell you you should do soil moisture like this, because you should, soil temperature like this, because it isn't. This is just to show you how it could be done using third-party data, to show you that KrigR can take all of these combinations. Now, before I wind down the workshop here and let you digest this information dump, I would have one request, or I would ask you to, if it's not too much trouble, when you sign off, just follow the link that I just copied into the Zoom chat, which will take you to a feedback form. It would be immensely helpful for us, because we're still trying to make this package better and better. If you could just give us a short, it won't even take a minute, just a short slider answer of how useful you think this was today, if you think you'll be using this, if you think you'll recommend this, what kind of functions you like, what kind of functions you would like to see, and if you have any other input. This just gets all sent straight to my email. This is completely anonymous. It would really help us a great deal. And if you've got any more questions, and maybe even some questions you want to talk about after everyone's left, you can just stay on. I'll be here for a while longer. Richard should still be here with us, so if you have some more questions towards him, let us know. Otherwise, if there's nothing else, I would just like to say thank you for coming here. This was my first big workshop I led, and this was a lot of fun. Thank you very much.